So one more example of being able to use a power series to approximate the value of a definite integral. So we have 0 to 0.2 of e to the minus x cubed. Just like we did before, it's probably helpful for us to remember what the power series was for e. All right, and we go back up here, and e to the x was series x to the n divided by n factorial. So we're going to replace x to the n with minus x cubed. All right, so we have to go through, and so remember, e to the x is going to be equal to the series n equals 0 to infinity, x to the n divided by n factorial, which implies that e to the minus x cubed is going to be equal to series n equals 0 to infinity of minus x cubed to the n divided by n factorial. And so if we write out some of the terms of this, all right, so that's going to be substituting 0 back in, that's going to be a 1. Substituting a 1 back in, that's x cubed over 1. Substituting a 2 back in, that's going to be x to the 6th over 2 factorial. Substituting a 3 back in, that is going to be negative x to the 9th over 6, which is 3 factorial. X to the 12th over 24, it's 4 factorial. And then just one more term, just so we can say that we did it, x to the 15th over 120. All right, now there are more terms in this series, but let's just go ahead and see if we can integrate those and see how close we can get to the actual value by using Wolfram alpha. And so we're going to say that the integral from 0 to 0.2 of e to the minus x cubed dx is going to be approximately equal to the integral from 0 to 0.3 of 1 minus x cubed plus x to the 6th over 2 minus x to the 9th over 6 plus x to the 12th over 24 minus x to the 15th divided by 120 dx. And so when we integrate term by term, we're going to end up, and this is a 0.2 by the way, that's going to be x minus x to the 4th over 4 plus x to the 7th over 14 minus x to the 10th over 60 plus x to the 13th, and then 13 times 24. So just use a calculator real quick. So 13 times 24, that's 312. Right, so that's 312. And then finally, x to the 16th, and 16 times 120. So 16 times 120, it's 1920. All right. And that goes from 0 to 0.2. So at this point, we could just substitute 0.2. 0 is going to cancel everything out, all right, because everything's a polynomial. So this becomes 0.2 minus 0.2 to the 4th over 4 plus 0.2 to the 7th over 14 minus 0.2 to the 10th over 60 plus 0.2 to the 13th over 312 minus 0.2 to the 16th over 1920. Now, I'm just going to go ahead and use my calculator to be able to approximate that. All right, so just give me a sec and I'll plug that in. All right, so let me clear this out. And I'm going to just minimize this just a little bit. So 0.2 minus 0.2 to the 4th over 4 plus 0.2 to the 7th. It should be to the 8th, excuse me, this last term. I think I might have forgotten to integrate some of these. Oh, no, I didn't. I'm sorry. I was looking up here and I thought I didn't integrate these terms. So we're good. All right, so going back here. So divide 14 minus 0.2 raised to the 10th over 60 plus 0.2 to the 13th divided by 312. And then minus 0.2 raised to the 17th divided by 1920, I think it was. All right, and it was 16th power. 16 divided by 1920. All right, so this is the value that we get, 0.1996, etc. All right, assuming that I punched everything in correctly, which I do believe so. So let's see how close we got to what Wolfram Alpha might say. All right, so bring up Wolfram Alpha again. Still have the same command that I did for the arctangent. So this time we're going to have exp to the minus x cube from 0 to 0.2. All right, and we got 199,601. And right here, we got 1119601. So we are in really good shape with this one. All right, so this is approximately 0.1996009.126. Our computer algebra system gave us 0.199601. All right, so that's really, really close. And remember, the computer algebra system is just rounding it off to 6 decimal places. So we can say that we're done with this. Okay, so that's how we can use power series to be able to evaluate or at least approximate our definite integrals. And the good news is we're finally done with power series for a while. Okay, so the next thing we're going to do is we're going to move into a completely new section. It's the final section of the course where we start taking a look at something called parametric sorts of functions, and then we're going to look at polar functions as well.